what's up, guys? So let's solve this interview question. So hope you guys subscribe to my channel. So a bug crosses a long edge of regular tetrahedron ABCD with edge length 1 is star and A, and each vertex chooses next edge at random. So it has 1/3 chance of going back along edge, comma, and 1/3 chance of going along each edge of other two. So find the probability that after it's crawled and the distance 7, it is again at A. Okay, so we can try to solve this in general. Okay, so I will give you two solutions. Okay, so first one is very let's first explain the problem. So we have A, B, C, D, and we have a bug. Okay, so bug will move 1/3 to B, C, D, and once it's maybe it's at B, it will go to A, C, D. Maybe it's D, then you can go to A, B, C. It's D. Maybe it's at C, it will randomly choose one of A, B, D. Okay, so the first solution will be very simple, just like the high school solution. Is that so let's go solution 1. So I can define Pn to be the probability of n steps. So n steps means that edge distance is n. A probability of steps going back to A. Okay, so I want to find the Pn plus 1. Okay, so what is Pn plus 1? Pn plus 1 is that after the n plus 1 steps, that it reach A. So that means at n steps, it must be one of B, C, D. Because if it's at A, if it's at n step is at A, then it cannot come back to A. Okay, so it must be 1 minus Pn, right? 1 minus Pn and take 1/3. So 1 minus Pn means that at n steps, it cannot hit on A. It must at B, C, D. And if it's at B, C, D, you have 1/3 chance to go back to A. Okay, and our boundary conditions or initial conditions, P0 is 1. Okay, so let's start to solve. Okay, so very simple. Where P1 is 1/3 times 1/3, and the P2 is just 2 divided by 9, and the P3 is just 7. P4 is just very stupid. Just keep iterating, and don't worry. I will give you the general end solution. Once I finish this stupid calculation. So I think it's 61. So it's 61 divided by 243, and this is P1, P2, P3, P4, P. Let's see, P1 is sorry, I'm stupid. Okay, I'm stupid. Sorry. So this should be P2, P3, P4, P5, P6, because P1 is just, sorry, I'm stupid. P1 start from 1/3, 1 minus P0, right? So it's 0. Okay, so yeah, P1 is 0, and then P2, P3, P4, P5, P6. Okay, so now let's go back to P7. So it's 1/3 times 243, and this is 182. So answer will be 182 divided by 729. I think so. Very tired. Okay, so this is our simple our first solution. Okay, so let's see for how to solve for January. So our goal is to solve January. Okay, so this is our transition equation. Okay, so in order to solve this problem, it's very simple. We use the technique that we use the ansatz. So let's suppose our ansatz is that Pn plus 1 minus alpha equals to beta Pn minus alpha. Suppose one can find alpha beta such that this equation is true, then you can see that this equation will tell you that P1 minus alpha equals to beta P0 minus alpha, and P2 minus alpha will give you beta P1 minus alpha so will be beta squared p0 minus alpha. So in general, you can show that Pn minus alpha will be beta n p0 minus alpha. Okay, so the only thing we need to do is just solving this alpha beta. So we just combine these two and see what this alpha beta is. So from this we have this Pn plus 1 equals to beta Pn minus alpha beta plus alpha. Okay, so beta will be minus 1 divided by 3. And then we get alpha divided by 3 plus alpha equal to 1/3. So alpha will be 1 divided by 4. Okay, so combine this. Finally, we get our Pn equals to beta to the n p0 minus alpha plus alpha. So will be this. So p0 is 1, right? So alpha is 1 divided by 4. So it's 3 divided by 4 plus this. Okay, so this is our first solution, general solution. Okay. Okay, so let's talk about the solution 2. If you have more background on the statistics or the probability theory, then you will know idea called the Markov chain. So basically, Markov chain means you have find some finite states, and at each time step there will be a transition probability, and that transition probability is independent of the time. Okay, so in this picture that we simply have PA, PB, PC, PD. We have four states, and our transition probability is that at PA that I have no way, right? I must go to BCD. So it's this 0, 1/3, 1/3, 1/3, and for PB is this. For PC, for PD, okay, so this is ABCD. So the computation is very simple. Let's call it M. So our goal is to compute N to the 7, or in general, we want to compute M to N. And once we compute N to N, it's very simple, right? Because our starting point is 1, 0, 0, 0. So the probability that it remains at A will be the first 1, 1 coefficient. So basically just this, right? This times this. So our results, so our answer will be this N to the matrices to the 7, the first 1, 1 matrix coefficient, or in general, so in general will be N to the N, N to the N to this 1, 1 coefficient. Okay, so now go back to your undergrad's linear algebra. Okay, so how to find N to N trick. Okay, so very simple. So let's write M to be 1 divided by 3 C minus I. So I will be identity. So it's identity. I'm stupid. So this is identity matrices 4 by 4. And the C is another matrices 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So obviously that if you C minus I, the diagonal term will disappear and times 1/3 that you get N. Okay, and we want to compute N to N. Okay, so there's a computation very simple, is that if you do C squared, you get 4C. And then you can check that if you go to the C to the N, it becomes 4 minus 1C. Okay, so our goal is to compute. We have this. Okay, so let's do the power N. Let's do power N. So we have N to N. Okay, so the tool that we have to use is binomial expansion. So we get N choose K from 0 to N, minus 1 N to the K, N to minus K, C to the K. Okay, so this is binomial expansion. Okay, so now let's take out the K equals to 0 term. For K equals to 0 term, then I get 1 divided by 3 and then minus 1 to the N with identity, right? Because K equals 0, then I get, so let me just write down the results, write down the rest term. Okay, so now I replace this C to the K to be 4K minus 1C. Okay, so I get -1 to n divided by 3 to n plus 4k minus 1c. Let me just write it this way. I can pull out c, right? I can pull out c. So I pull out c and then put my c here. Okay. So it becomes this. Okay. Now, I want to combine this as another binomial. Okay, so I delete this and divide by 4. Okay. Okay, so now the results will be -1 to the n, 3 to the n, plus c divided by 4. Okay, so these terms, I want to complete as a binomial, right? So I want to take k equals to 0. Okay. So I want to take this. So I can write as k from 0 to n and choose k -1 and choose k 4 to the k minus k equals 0 term. Well, so k equals 0 term will be what? Will be 4 to the. Okay, so will be let's see. Sorry. Oh, I did some stupid thing. When I do this, I did a stupid thing. I should make this 3 to n here. Right, because this 3 to n should expand. Okay. So when I minus this, then I should take out the I need to minus k equals 0 term. Okay, so k equals 0 term is just what? It's just 1, right? K equals 0. Sorry, k equals 0, then I get -1 to n. Okay. So now this will be what? So this will be -1 and minus k 4 to k, right? So in you can write as 3 to the 8. Use a binomial expansion. Okay, so finally your n to n will be what? Minus n divided by 3 plus c divided by 4 3 to the n, and that is will give you 3 to the n minus -1 to n. This to be correct. Yeah, should be correct. Okay. So what is this? So your m to n will be c divided by 4, right? This is this term. And then you got another 2 term, which is -1 to the n divided by 3 times identity minus c divided by 4. This term come out with where? So it's you do this, right? And then you jump into this. So yeah, and you take out -1 to n, so you get another c divided by 4. Okay, so this is your answer. Okay, so what's n to the n? 1, 1. 1, 1 means the 1, 1 coefficient. So C11, C11 is 1 plus -1 divided by 3 to n, and the 1, 1 is 1, right? So 1 minus 1 divided by 4. So this 1 divided by 4 plus -1 to the 3 divided times n, 3 divided by 4. Okay, so let's go back to see where they are the same. Nice, exactly the same. Okay. Okay, so these are 2 solutions. Hopefully you understand this question. Okay, see you guys next videos.